Hi guys, the next thing that we are going to talk about are transformations with our various functions. Okay, so we have talked about a lot of different functions and we have talked about, what a parent function would be for a particular type of function. All right, all of our functions are taking the parent function and we're building off of them. We're making some sort of transformation to that parent function to get a different function. Okay, so now what we're going to look at is how we take the parent function, and depending on how we adjust that function, what transformation occurs or what actually happens to that function. Okay, so the functions that we have looked at. So these are like the most basic functions. These are the ones that are always being built off of or transformed somehow to get other functions. We have linear functions. So the parent function of a linear function is y equals x. We had a quadratic function. The parent function of a quadratic function is y equals x squared. Then we have an absolute value function that we looked at, y equals the absolute value of x. We looked at exponential functions. We have other functions also, like you have a square root function, you have cube root function. Okay, there are other functions out there, but these are the ones that we have looked at this year. Okay, so let's look at what happens if we make certain adjustments or if we alter our parent functions. Let's see what ends up happening to them. All right, first thing is anytime, so when you see this f of x right here, that's saying, okay, regardless of what function we're looking at, if I said f of x equals x, that would be our linear equation. If I said f of x equals x squared, so if you're taking your parent function, and it doesn't matter if it's linear, quadratic, the absolute value function, I'm going to take that parent function, and if I add a positive k value to it, so let's say I add 5, regardless of what the function is, what happens to that function? Okay, let's take a look. Let's say I had the linear function y equals x. Okay, let's see what would happen if I add 5 to it. What ends up happening? So this blue line is the parent function, and the green line, or the red line is what has happened after I have changed that function, after I have added on 5 units to it. Now notice it's a parallel line. It's the exact same line. It is just shifted up. And it's shifted up the 5 units, that k value that I added on. Okay, let's say instead of adding 5, let's say you add 9. Well, what happens to it? It shifts the graph up 9 units. All right, let's say you had a quadratic equation. So let's say we took our quadratic and we do the same thing. Let's say we add 9 units to it. So I graph it. So the blue is your parent function, the x squared. And you'll notice that I have, let me adjust my window a little bit. Oops. I didn't mean 2, I meant 20. Oops. Okay, you'll see that the blue is the parent function, and in red, it's the exact same curve. It's just shifted up 9 units. Okay, so what the rule is saying is that if you have a function, whatever your function may be, let's say we have, we're going to call this new function g of x equals, take these away, equals that parent function, the f of x, regardless of what it would be. If I add 5 units to it, I'm shifting it up 5 units. In this question, it's saying an example. If the graph of the function f of x equals 2x or 2 to the x power, so that's your parent function, your parent exponential function, and it undergoes a translation of 5 units up. So what I could say is I could take that parent function and add 5 to it. What would the new function be? So we would say that this is, so f of x is 2x plus 5. Okay, whatever function you start with, you're just adding 5 units to shift it up. Okay, so that's talking about a vertical translation. It's just going to shift it up. Now, same thing happens if k is less than 0. So here's your parent function. What do we think is going to happen? So if that k value is less than 0, that means that you're subtracting from the parent function. So instead of adding 9 or adding 5, I'm going to show the example by subtracting. Let's see what happens. And I'm going to have to, okay, that's okay. It takes that function, it's the exact same function, and it's just shifting it down however many units k is. Okay, so anytime you take that parent function and you add or subtract a value to that initial equation or initial function, it's going to shift your graph up or down. Okay, so an example, it says the graph of function f of x is x squared. So we're dealing with that parent function of a quadratic. Undergoes a translation of 7 units down. What is the new function? So we could call the new function h of x. And what this is saying is that if I take f of x, which is x squared, and I shift it down 7 units, that means I'm going to subtract 7. So my new function is f of x is actually x squared, and then I'm going to subtract 7 from it. I'm shifting it down 7 units. Okay, so that's a vertical translation. All right, horizontal translation. Horizontal translation, it's saying if you add h to the x value of a function where h is greater than 0, then the graph of the function will shift to the left. Now, this is really important. It's kind of like the opposite. Okay, if we look at our graph, so our parent function, let's say we use x squared. Now, you are making an adjustment to the actual x value. So it's before you're squaring it. So let's say I said x plus 5, and then I'm going to square it. Let's see what happens to the graph. Notice how it shifts to the left. Okay, think about when we went through and we were solving quadratics. Our quadratic equation, the parent function x squared, starts at 0, 0. Okay, so if I take my x value and I'm adding 5 to it, if I'm adding 5 to it, I want to know what's going to bring me back to 0. Okay, if I have the equation y equals x plus 5, all right, I want to know my parent function initially starts with y equals x squared. So 0 squared is 0, 0. This is saying, okay, I'm going to add 5 to my x first before I square it. So in order to bring this back to that parent function, back to 0, 0, what does x have to be? X has to be negative 5. All right, it's shifting it to the left 5 units. Okay. An example up here, shifting it to the left 5 units. An example of this, the graph of the function f of x equals the square root of x. This undergoes a translation of 4 units to the left. What is the new function? All right, so I'm going to call my new function g of x. G of x, it's saying that I'm going to shift it to the left, So I'm going to think, all right, I'm going to take my x value and I'm going to add 4 to it. So my new function, g of x, since that function f of x is the square root, now I'm going to add 4 to that, okay? If I'm going to the left, that would bring me to negative 4. How am I going to bring it back to 0? I'm going to add 4. Let's look at, let's say you had just a line. If I have x plus 4, let's see what happens. See how I've just shifted to the left 4 units? So any time you add to the x value before you apply the, whichever type of function you're dealing with, you adjust the x value first, you're going to think the opposite, and that's what's going to move you to the right or the left. And that's what letter D is. Letter D is saying, okay, well, what if this time I subtract from my x coordinate? Okay, if I subtract from my x coordinate, what would happen? Well, let's go back to this linear function. If I subtracted 4, what happens? It shifts it to the right. Okay, so for both of these, you're going to think opposite. Think opposite. Okay, if you had an absolute value function, okay, let's look at the absolute value function. All right, let's do just the regular parent function, the absolute value of x. Let's do the absolute value of x. And now remember, we are going to add or subtract to our x value before we apply the absolute value to it. So let's say x plus 5. And let's see what happens when we do x minus 5. Okay, if I go to graph this, so the blue is the parent function. Red is when we added 4, and notice how it shifted to the left, so it goes in the opposite direction. And then the black is when we subtracted 5, so it shifted it to the right. Okay, so in our notes again, the graph of the function f of x equals the cube root of x. It undergoes a translation of 8 units to the right. What is the new function? So I'm going to think, new function, I'm going to call it g of x. I'm taking the function f of x, and since I'm going horizontally, I know that I'm adding or subtracting to the x value first. And since this one is shifting to the left, I'm going to think the opposite. Okay, if I go to the left, that means I'm going to shift to -8 as where it starts at. So I am going to have to add 8 to that. All right, so my new function, I could say g of x, and since it's the cube root of x, I'm going to plug in x plus 8. So that's going horizontally. Horizontally, you are adjusting the actual input value, the x value. You are adding or subtracting to it depending on which direction you want your graph to shift. Okay, vertical scaling. Vertical scaling means, is the graph going to get skinnier or is it going to get wider? All right, we looked at this a little bit when we talked about quadratics. Let's put in the calculator. Let's see what happens. All right, let's go to, we can do that absolute value function again. So we are going to do the absolute value of x. This is saying if my a value, what I'm multiplying my function by, if that is greater than 1, the graph will become narrow. So let's put in a number that's greater than 1. Let's do 3. Times the absolute value of x. Let's see what happens. So I graph it, and notice how it gets skinnier. So this will be the same case no matter what type of function you use. Okay, if I had, if f of x, I put in the calculator the absolute value of x, but if I did 3 times x squared, so that would mean that f of x was x squared, that would also get skinnier. Oh, look at that. That's my next example here. So the graph of the function f of x equals x squared is vertically stretched. It's made narrow by a scale factor of 3. What is the new function? So I'm going to call my new function g of x. And since this is a vertical stretch by 3, I'm going to take 3 and multiply it by f of x. So now what would my new function be? g of x equals 3 times f of x. Well, f of x was the function x squared. All right, so that would represent a vertical stretch. What would happen if you multiplied the function by a number that was between 0 and 1? What happens to the function? Well, it will always become wider. And let's see why. Or let's look at an example here. So using the absolute value function, I'm going to do a third this time. Times the absolute value of x and graph it, and let's see what happens. See how it becomes much wider than that blue, that parent function in blue? All right, that always happens regardless of what type of function you're looking at. Okay, so looking at our example, it's saying, again, we're going to use the function f of x equals x squared, and now we are going to make it wider by a scale factor of 3. What's the new function? So I'm going to call the new function g of x, and if I'm going to make it wider by a third, I'm going to do 1/3 times f of x. Okay, so to write my new function, g of x will equal a third times f of x, and f of x was x squared. Okay, all right, that's vertical scaling. So it's either going to become skinnier or wider. Horizontal scaling. Horizontal scaling means that it is going to, we're going to multiply our actual x value by a number that is greater than 1 or by a number that is in between 0 and 1. And we're going to see what happens. All right, let's go back to, let's use that absolute value function again. All right, so if I multiply my x value by a number that is where you have 1 over a is greater than 1. So that means I actually end up with a fraction. Let's see here. So if I multiply that x value by, let's say, 1/3, what will happen? And I want to delete this one for right now. Okay. I'm going to put both of these in here right now. If I multiply by where 1 over a is greater than 1, I got to go back up here. So let's say I multiply, I multiply by 1 over a, the actual value of 1 over a is greater than 1. So let's do the absolute value. Let's do 3x. And then my other equation, that the 1 over a sorry about this. All right, so now let's see what happens when I multiply by a value that is less than 1. So for example, 1/3, we could say. Let's see what happens. All right, graph it. All right, so in blue is the parent function. All right, in red is where I had 3 times my x value, where that the value of 1 over a actually ended up being greater than 1. And in in black is where I was multiplying x first by a third. So that 1 over a value was less than 1, but greater than 0 still. And that made it wider, horizontal scaling. All right, let's look at the graph of function f of x is the absolute value of x. Oh, I just did this. Is horizontally compressed or made narrow by a scale factor of 1/3. What is the new function? All right, so in this case, I have g of x equals. Now, this is saying that if 1 over a is greater than 1, all right, greater than 1. So in this case, 1 over a ends up being greater than 1. It's saying my a is 1/3. So this actually means 1 over 1/3, which equals 3. So this is saying the function f of 3x. So g of x equals, in this case, I'm using the function, the absolute value of x, but I'm putting in 3x, and that's how I get skinnier. All right, the next example, and this is also the one that I put in the calculator already. I didn't realize this is what I used for my examples. G of x will equal, and now this time it's saying that your a value has to be greater than 0 but less than 1. Well, in this case, my scale factor is 3. Well, 1 over a equals 1 over 3 if a is 3. So I do have a number that is between 0 and 1. So if I multiply my x by 1/3 first, what happens? It gets wider. And I can call that function g of x equals, and now f of x was the absolute value of x, but now I'm finding f of 1/3 x, so f of the absolute value of 1/3 x. Okay, so think if you have 1 over a, so if that scale factor is, it ends up being less than 1. Think like opposite. All right, if that value of 1 over a ends up being greater than 1, it will be a vertical stretch. If the value 1 over a is less than 1, it will be it'll make it wider, a horizontal stretch. Okay. All right, last one is a reflection. All right, so when something is reflected over the x-axis, what will happen is you will take the whole entire function and you are just going to multiply it by -1. Okay, you're going to negate the function, and that will flip it over the y-axis or over the x-axis. And I'm going to go back to, just so I don't have to type in this absolute value all the time. Let's say you had the function x squared. Okay, now watch what happens. If I multiply x squared by negative, look at how it just flips that graph over the x-axis. Okay, so if we look at the function g of x, it says graph the function f of x equals the square root of x. If this is reflected over the x-axis, what is the new function? So I'm going to call my new function g of x, and I remember that if I have a function f of x and I just multiply it by a negative, that will flip it over the x-axis. So my new function, I'm going to do negative. Now what was f of x? The square root of x. So that would be my new function. Okay, so to flip over the x-axis, we just multiply the whole function by negative, or by -1. Okay, all right. How do we get it to flip over the y-axis? Well, in order to flip over the y-axis, you are going to negate the input or negate the x value. So if I go back to my function, so here I was multiplying the whole function by -1. Well, now I want to multiply just the x by, and you're not going to see it with a quadratic here. Let's go, let's do y equals x. All right. So if I multiply, you're not going to see it with that one either. You'll see it with the, let's do this one. Okay, so if I have my basic y equals 2 to the x power, if I negate my exponent, oops, let's see what happens. So notice how when I made the x negative, it flipped over the y-axis. If I make the whole equation, if I multiply the whole equation by a negative, notice how it flips it over the x-axis. See the difference, okay? All right, so the blue was the parent function. Nope. Oh. For some reason, it's not showing up now. The blue was the parent function. The red was the, it's frozen. All right, the blue was the parent function. The red was after the x was multiplied, and that flipped it over the y-axis. And then the black was when we multiplied the whole function by a negative, and that flipped it over the x-axis. So right here it says the graph of the function 2x is reflected over the y-axis. What is the new function? So if I call my new function, let's say h of x, I remember to flip it over the y-axis, I'm going to multiply my x value by a negative. Okay, so when I go to write this new function, I'm going to think h of x equals, and so if my function is 2x, that was f of x, but I'm going to negate the x value. So 2 to the negative x would flip it over the y-axis. Okay, so these are your rules on how to translate different functions. Okay, let's say I gave you the equation y equals x, and I said I would like this to be reflected over the y-axis. All right, what you would do is we would just say y equals negative x. All right, let's say I gave you the function y equals x plus 1, or let's say we call this f of x equals x plus 1. And I said flip it over the y-axis. So what you would do is you would say, I'm going to make the x negative. So this would be negative x plus 1. Okay? Let's say I wanted you to flip this over the x-axis. If I flip it over the x-axis, remember you're making the whole function negative. So I would think negative f of x. So I would do negative x plus 1 in parentheses because it's the whole function. See the difference between those two? Okay. All right. So that was the last thing for this week. I will again also post these notes written out. If you have any questions, feel free to email me or ask questions during office hours at the end of the week.